Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Chapter 1, Theorems of Alignment and the Principle of Duality.
Section 9, the three space. Definition: if P, Q, R, and T are 4 points not in the same plane, and if pi is a plane containing Q, R, and T, the class S3 of all points on the lines joining P to the points of pi is called the space of 3 dimensions, or the three space determined by P and pi. If a point belongs to a three space or is a point of a three space, it is said to be in, or to lie in, or to be on the three space. If all the points of a line or plane are points of a three space, S3, the line or plane is said to lie in, or to be in, or to be on the S3. Also, the three space is said to be on the point, line, or plane. It is clear from the definition that P and every point of pi are points of the three space determined by P and pi. Theorem 8. If A and B are distinct points on a three space S3, every point on the line AB is on S3 by assumptions A. Proof: let S3 be determined by a plane pi and a point P. 1. If A and B are both in pi, the theorem is an immediate consequence of Theorem 4. 2. If the line AB contains P, the theorem is obvious. 3. Suppose A is in pi, B not in pi, and AB does not contain P, figure 10. There then exists a point B prime not equal to A of pi collinear with B and P by definition. The line joining any point M on AB to P on BB prime has a point M prime in common with B prime A by assumption A3. But M prime is a point of pi, since it is a point of AB prime. Hence M is a point of S3 by definition. 4. Let neither A nor B lie in pi, and let AB not contain P, figure 11. The lines PA and PB meet pi in 2 points A prime and B prime respectively, but the line joining A on A prime P to B on P B prime has a point C in common with B prime A prime. C is a point of pi, which reduces the proof to the case 3. It may be noted that in this proof no use has been made of E0. In discussing case 4, we have proved, incidentally, in connection with E0 and Theorem 4, the following corollary. Corollary 1. If S3 is a three space determined by a point P and a plane pi, then pi and any line on S3 but not on pi are on one and only one common point by assumptions A and E0. Corollary 2. Every point on any plane determined by 3 non-collinear points on a three space S3 is on S3 by the assumptions A. Proof: as before, let the three space be determined by pi and P, and let the 3 non-collinear points be A, B, and C. Every point of the line BC is a point of S3 by Theorem 8, and every point of the plane ABC is collinear with A and some point of BC. Corollary 3. If a three space S3 is determined by a point P and a plane pi, then pi and any plane on S3 distinct from pi are on one and only one common line by assumptions A and E0. Proof: any plane contains at least 3 lines not passing through the same point, by definition and assumption A1. 2 of these lines must meet pi in 2 distinct points, which are also points of the plane of the lines by corollary 1. The result then follows from Theorem 7. Theorem 9. If a plane alpha and a line A are not on alpha, are on the same three space S3, then alpha and A are on one and only one common point by assumptions A and E0. Proof: let S3 be determined by the plane pi and the point P. 1. If alpha coincides with pi, the theorem reduces to Corollary 1 of Theorem 8. 2. If alpha is distinct from pi, it has a line L in common with pi by Theorem 8 and Corollary 3. Let A be any point on alpha, not on L, by E0, figure 12. The plane AA, determined by A and A, meets pi in a line M not equal to L by Theorem 8 and Corollary 3. The lines L and M have a point B in common by Theorem 5. The line AB in AA meets A in a point Q by Theorem 5, which is on alpha, since AB is on alpha. That alpha and A have no other point in common follows from Theorem 4. Corollary 1, any two distinct planes on a 3 space are on one and only one common line. Assumptions A and E0. The proof is similar to that of Theorem 8, Corollary 3, and is left as an exercise. Corollary 2. Conversely, if two planes are on a common line, there exists a 3 space on both. Assumptions A and E0. Proof: if the planes alpha and beta are distinct and have a line L in common, any point P of beta not on L will determine with alpha a 3 space containing L and P and hence containing beta by Theorem 8, Corollary 2. Corollary 3, 3 planes on a 3 space which are not on a common line are on one and only one common point. Assumptions A and E0. Proof: this follows without difficulty from the theorem in Corollary 1. Two planes are said to determine the line which they have in common and to intersect or meet in that line. Likewise, if 3 planes have a point in common, they are said to intersect or meet in the point. Corollary 4. If alpha, beta, and gamma are 3 distinct planes on the same S3, but not on the same line, and if a line L is on each of the 2 planes mu and nu, which are on the lines beta gamma and gamma alpha respectively, then it is on the plane lambda, which is on the line alpha beta, by assumptions A and E0. Proof: by Corollary 3, the planes alpha, beta, gamma have a point P in common, so that the lines beta gamma, gamma alpha, alpha beta all contain P. The line L, being common to the planes through beta gamma and gamma alpha, must pass through P, and the lines L and alpha beta therefore intersect in P and hence determine a plane lambda by Theorem 6 and Corollary. Theorem 10. The 3 space S3 determined by a plane pi and a point P is identical with the 3 space S3 prime determined by a plane pi prime and a point P prime, provided pi prime and P prime are on S3, by assumptions A and E0. Proof: any point A of S3 prime, figure 13, is collinear with P prime and some point A prime of pi prime. But P prime and A prime are both points of S3, and hence A is a point of S3 by Theorem 8. Hence every point of S3 prime is a point of S3. Conversely, if A is any point of S3, the line AP prime meets pi prime in a point by Theorem 9. Hence, every point of S3 is also a point of S3 prime. Corollary: there is one and only one 3 space on 4 given points not on the same plane, or a plane and a point not on the plane, or 2 non-intersecting lines, by assumptions A and E0. The last part of the corollary follows from the fact that 2 non-intersecting lines are equivalent to 4 points not on the same plane, assumption E0. It is convenient to use the term coplanar to describe points in the same plane, and we use the term skew lines for lines that have no point in common. 4 non-coplanar points or 2 skew lines are said to determine the three space in which they lie.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.